Thank you for the invitation. And I'm Huixin Liu from Kyushu University, Earth and Planetary Science Division. And so before starting here, it's a little bit of history about me. And although it's written in Japanese, I hope you can read a little bit. And so briefly, I've been living in Japan for 19 years. So it's long enough for me to actually forget English, which is not my mother tongue anyway, as you have already noticed. But still not very long enough to learn the exquisite Japanese. I think you all have recognized that. So that's why I'm very glad that my task tonight is to talk about space weather, not language. Okay? And I do have a little bit problem with my voice, so I will try to shout. But if you don't hear, just feel free anytime raise up your hands. And so space weather, right? And how many of you have heard about this word? Wow, quite a few. 4 hands. And how many of you have, what's that? Okay. All right. So how many of you have heard about storm, magnetic storm, or Aurora? Wow, that's many. And with that, then I guess I don't even have to explain, right? So already you're no stranger of space weather. And so what is actually space weather? And maybe you want to move here? So well, to answer that, I would like to start with the weather. We are all familiar. And so every morning when I wake up, the first thing I check is actually the weather forecast in Tenki GP. And I guess maybe many of you do. But why do we check, or why do I check? It's because I want to know whether it's sunny or raining, and so that I can decide whether I ride my bicycle or take the bus to work. And and so well, I mean that's some reason. But more importantly, why do we check weather? And I think it's because the weather is changing, right? If it's every day the same, there's no need to check, and there's no need to forecast. And so actually it's the change that is called weather, okay? And similarly, so the space weather is the change in space, in a way. But this time is the space, particularly the near-Earth space we call the ionosphere. So this is the region, particularly in the range about from 80 to 1,000 kilometers. And this region is called the ionosphere. And well, similar to the weather affects our daily life. And actually the space weather, it affects let's say, the daily life of our satellites flying in this region. And as shown here, so, but different from the weather, and the ionosphere is made up of all kinds of plasmas. So this plasma, this sea of plasma, and is changing, from day to night, from one day to the next. And this is the space weather. So now the question you might ask, what makes this change for the space weather? And the answer is the sun. And with this, you might say, oh, wow, that's great. I know the sun very well. I see it every day, and it's 150 million kilometers from us, and it's soothing, and it's very calm. But that's the sun in our eyes, seen through our own eyes. But when we see through the eyes of our instruments, and it's completely a different thing, as you can see here. So on the left is the solar disk seen by the NASA Solar Dynamic Observatory. And you can see on the surface that there's nothing like a calm and smoothing. And it's with actually the solar flares exploding all the time, here and there, in a very unpredictable way. Okay? And with this, there are 2 types of emissions. Oh, oops, go back. There are 2 types of emissions from the sun. Maybe some of you already know. And so one type is the solar radiation, which most of us very familiar, including the visible light we can see every day. And so these radiations, they are so basic electromagnetic waves traveling at the speed of light. And so they can reach us in 8 minutes. And there is another type of emission from the sun is called the solar wind. And these are made up of energetic particles. And they travel much slower, as you can see. They're 500 kilometers. So with this speed, it takes about 3 days, actually, for them to start from the solar surface and to reach us on the Earth. And when they do reach us here on Earth, as you can see here, the solar radiation travels faster. And behind that, there's the solar wind. But when they hit the Earth, and they produce the space weather, actually, which we often also say is solar storms, magnetic storms, and they are basically the same thing, okay? And so, therefore, with these two type of radiations, I mean, the sun or the Earth, let's say, the Earth is, constantly bombarded by the strong radiation and also high energetic particles. And so we can see that the Earth is actually sitting in a very, very harsh space environment, like being exposed to the Fukushima melting, what was that, power plants, right? Okay, so it's a very harsh space environment, but we are all still alive, right? We are all okay. So who is protecting us?
Is it the Earth?
Who is protecting us? Superman, right? So we actually have two Supermen, not only one. One is the Earth's magnetic field, and the other one is the atmosphere. And the Earth's magnetic field, as you can see in this little sketch here, and it basically deflects the energetic particles and make them detour to go around the Earth instead of hitting us directly. And for the other Superman, the atmosphere, it tries to basically absorb the very dangerous radiation like X-ray and ultraviolet. And so that only the very life-friendly visible light can reach the sun's surface, can reach the surface. Okay. All right. So here's a very nice movie I would like to show from NASA website, and it shows the whole process of what caused the space weather. So this dynamic process here. So you can see the solar winds, they leave the Earth's surface and reach the Earth, but being detoured or deflected by the Earth's magnetic field. So most of them will not reach us, right? Will not hit us there. Okay, so now you know what is space weather and what caused space weather, right? So you might ask, okay, can I see space weather? Like I can see the weather, I can feel the weather by looking at the cloud and feel the wind. How about space weather? And the answer is yes, you can see space weather through aurora. So the aurora is actually the visible form of space weather, or actually it's the only visible form of space weather. And the auroras are actually caused by energetic particles in the solar wind, okay? But maybe some of you already noticed, you might say, wait a minute, just last slide, you said the magnetic field is protecting us from the energetic particles coming in. How come they are producing aurora on the Earth? So here the point is the protection is not waterproof. So there is some leak or leakage of the energetic particles. And it's these leaked energetic particles into the Earth environment that is causing the aurora, okay? And then here I have a quiz for you. And so if you want to go to see aurora, and where do you want to go? Where can you go? If you want to see the beautiful aurora, where do you go? right? Alaska and Canada and all those high latitude.
But the other day it was.
Yes.
Oh, sorry.
Absolutely, that's the good point. So I will come to it. So why do we? So basically, when we want to see aurora, normally we go to high latitudes regions, right? High latitude countries, and the reason for that is because the answer is in this sketch that leakage, this leakage, normally it happens in high latitudes, okay? Because the magnetic field in high latitudes, they are open instead of closing. So therefore, it's very easy actually for the energetic particles to come in because they are open, okay? That's why you see aurora normally in high latitudes. But of course, and when the solar storm is so strong, and this aurora region or this open field line, they kind of expand to the mid latitudes, like in May this year. And in this case, you can also see aurora in mid latitudes, right? Japan, even a lot of people see, I think, and many people in Europe, like Germany and France, they also see. So I think one of my friends said in Kobe they also see aurora, which I'm not sure, but anyway, and so in this kind, if the solar storm is very strong, we do have a chance to see here. And by the way, so if you are a fan of aurora, I guess many are fan of aurora, right? You might want to check out this website called the Aurora Surveys. And yeah, this is a website for citizen science supported by NSF and NASA. And on this site, you can see you see not only extremely beautiful aurora photos, but they also provide prediction or forecast of aurora. So where you can see aurora, and they will give a map saying here and here and here you can see. So during these space weather events, and you might want to check out this. And okay, so you say if I'm no fan of aurora, should I still care? Should I still care about space weather? And the answer depends on how you want to live. Okay, our topic, to live. And if you want to live like our monkey ancestors, like a caveman, or maybe also indigenous people, I don't know, and you don't need to care, okay? No need to care about space weather unless you want to watch the aurora. But on the other hand, if you want to live a little bit more comfortable like this, and I guess you have to care, because behind the aurora, actually there is a huge energy which can disrupt our modern technology. And talking about huge energy, so first here I would like, let's have a look at how much energy is released during a solar storm from the sun. Any of you can imagine? So to get a feeling, I would like to have a comparison with the energy released by the atomic bomb dropped in Hiroshima. Okay, that's a huge energy, right? And suppose we can express the energy in the size of the ant, okay? And then the energy released during the Tohoku earthquake will be the size of the cat. And the energy released during a typical solar storm will be the size of an elephant. So with this, I guess you can already imagine how much impact it will have on the Earth, right? Okay, so the energy, when the space weather events or the solar storms, when they reach the Earth, they have a very direct impacts on the space environment, particularly near Earth space environment, and also direct impacts on all the flat satellites that fly in this environment. And so they can immediately, make the satellite deviate from their predicted orbits or even crash into each other. So with this, I guess many of you have already maybe still heard the news in 2022 that about 40 Starlink satellites actually fell out of the sky during this storm. The reason was because there was a storm. And of course, with all these damages to our satellites, and you can imagine that there will be a very strong disruption to the communication and navigation systems, because these are strongly depending on all these satellite networks, right? And therefore, when you have these communication disruptions, so of course, not only we ourselves will get lost on the way to some party or to here, but also our cows and lamb, because these are nowadays, they are located by GPS sensors, actually. Every little animal, they have a little sensor in their neck. And also on larger scales, more seriously, and this communication and navigation disruptions, they do affect the airplane safety and also the rescue activities, and they also affect traffic control. All these train networks and plane networks will all be affected. And if you think those are still far away from you, and this one you won't miss it. And because space weather, when the storm is so strong, it also affects the power grid, right? Just like, this one is a very famous one in 1989, that a March storm caused a very large-scale blackout, actually, in Quebec region. So this can leave, millions of people without electricity. Okay, so with this, we can see that although the aurora is very beautiful, but behind that is really all these kind of distractions and disruption, and therefore you can see aurora, although everybody love it, is actually not a good sign. And interestingly, and this coincides with our ancient non-scientific understanding of aurora. And for instance, as shown in many historical records 2,000 years ago, like paintings and the diary from the Imperial Observatory, and they all regard this aurora as an omen for disasters and even for wars. Okay. Although they didn't understand, but they could see, aurora didn't just come only in modern age. It has been there millions of years. And okay, so with all these disruptions, particularly these negative impacts, and I think it's very easy to understand there is a very strong need for space weather forecast. And so all this science community and also governments, we all recognize this need and are working hard to forecast the space weather. So you might wonder what a space weather forecast look like, right? So here is one from NOAA. NOAA is like a space weather agency in the US. You can see, Monday, solar wind low and chances of aurora low, and Tuesday the same, and Wednesday high. So what's your comment on this space weather prediction or forecast?
You can still take your bicycle to work.
Good. So yeah, very simple, right? Almost useless in a way. Yeah, so that's exactly true. I mean, compared to the weather forecast, and space weather forecast still has a very, very long way to go. But it's a very fast developing field, and our final goal is the same. So we aim to be able to provide not only this when and where a disruption will occur, but also how strong the disruption will be and how long that will last. And so basically my lab is to help achieve this goal, and we are conducting some basic research on space weather. And at the same time, we also help to bring up the first generation space weather forecasters. So if any of you want to become one, come to join us, okay? That's the message I have today. Okay, thank you so much. Any questions?
Fantastic. Go ahead. Oh, yeah, you can pick
Yes.
Is there any impact of the space weather on the Earth's weather?
Impact of space weather on the earthquake.
Yeah, on the Earth's weather.
On the Earth's weather. Yes, yes, there are. There are quite a few types, and one is these energetic particles, because they come right. They come in, when they come down, and they destroy the ozone. So they affect the climate.
Oh.
And yeah, that's a very nice point you are asking. Where is it? Yeah. So. Right. Right, because these energetic particles, they really come down very deep to the atmosphere, because the magnetic field lines are open, so they come down, and then they destroy the ozone, and sometimes even go further down, and so they do affect the weather.
They don't have an impact on the actual clouds formation?
Clouds formation.
Some hypothesis about sometimes
Right.
possibly having a connection with solar flares.
Right, and that's the cosmic ray. The cosmic ray affect cloud, but the cosmic ray, of course, is from outer space. But there is also because the solar wind is there, and they sort of tend to block part of the cosmic ray. And when the solar wind is disturbed or getting stronger or weaker, so they do affect how much cosmic ray are coming down to the Earth. So in that way, it does not directly affect the wind, the cloud, but it modulates. It modulates, maybe, yeah, kind of modulates.
Most of the things you mentioned, like the Aurora and the effects on Earth, must
Right.
be solar wind. But you also mentioned 1989 was magnetic storm. Is that solar wind or solar flare? 1989, what that?
The 1989 for the blackout, that's
Yeah.
also solar wind.
Solar wind.
Yes, solar wind. Yeah.
Thank you.
So the flare does also affect. The flare has an immediate impact, 8 minutes, and so mostly it's on the radio communication. So particularly if you're communicating from the airplane to the ground station, and if there is a flare, the signal will immediately drop because it will be absorbed. So that's.
Yes, huh? Yeah.
So when we talk about this, weather on Earth,
Yes.
really, the time of unit, the unit of time
Unit
is
of
day and season.
Yes.
But it's the same as the solar weather, the time of unit,
Space weather.
space weather.
Oh yeah. Space weather, it's also changing from day and night, and it's also that. But sometimes it's much faster. It's in seconds and minutes, because of these solar flares and processes in the magnetosphere or ionosphere, because they are plasma and charged particles. They are much more mobile, and their reaction is much faster. So
Are there longer variation of the solar activities and
solar activities are very long. So let's say the orders expand much wider than the Earth's weather. So I mean, the space weather, they expand, from solar cycle is 11 years, right? And then down to, of course, also season and minutes, even seconds.
How accurate is the prediction right now? I mean, the 40 lost satellites from SpaceX and some a very big deal.
Right. The prediction is not high. Yeah, that's why there were 40 fell out of the sky, right? So I think it's really low. I don't know how do normally there is we call it a score. There is a score like if you hit if you are true, and then you are like 100% score, right? But if you completely fail, it's like 0. And so the scores, let's say there are, normally when we evaluate score, we compare with one type, we say today's space weather will be same as tomorrow. So, and with this, then we also run our models and produce a forecast, and then we compare with this say it's same as tomorrow, right? and it almost doesn't make much difference. So you can see the level is really very low. That's why we have to work hard. Yeah, try to get some better forecast. Yes.
Yes.
Oh, okay. It's really simple question, but
Yes.
is space weather really weather? Because you are talking about some
Change.
projection of some particle from the sun
Yes.
or the
Yeah.
movement of magnetic field.
Yes.
But it has nothing to do with weather we usually kind of feel on the Earth.
So the weather is, we say, what is weather? Weather is changing, because it's changing from one day to the other. And it's this change is called weather, right? So that's why we say similarly, because the outer space is also changing from yesterday to today and from today to the next day. That's why we call it weather in that kind of definition, in terms of change. So anything change is weather. If it doesn't change, it's not weather. Even here, if the weather tomorrow raining, next day raining, 365 days raining, it's not weather. Because it doesn't change anymore.
So
Right?
am I
So,
feeling
so,
weather?
so it's the change we call it weather. Okay?
Instead
Yes.
of raining water, it rains particles.
Yes,
It's
yes,
raining.
yes. That's a good way. Raining particles. Yeah. Yes.
So if a person who predicts weather on Earth is a meteorologist, what's the term for a person who predicts space weather?
Sorry, I didn't understand. Mean the word.
If a person who predicts the weather of the planet is a meteorologist, what's the term for a person who predicts space weather?
Oh well, that's still not determined. So we call it space weather forecaster, right? So well, I just call it space weather forecaster or space meteorologist, right? Does that make sense? So in Japanese, it's pretty easy. In Japanese, yo tenki yo hoshi, right? Tenki yo hoshi. So we just say uchu tenki yo hoshi. So that's.
Still got about 3 more
So-
minutes. Sorry.
Go ahead.
What do you do if you have a prediction for fairly aggressive space weather? What do you do on the surface? What do you do on the satellite to prevent damage?
Right. That's exactly the point of making space weather. That we want to take action, right? And so normally, if you predict a very serious one, and you can switch off your instruments on satellites, and because most instruments they have a safe mode. If they are not working, if you switch off, and then they are less vulnerable to energetic particles and things. Yeah. But satellites and the orbit, that's very difficult in a way. Okay. So here, this is I prepared a little question just in case nobody asks. So does Totoro care about weather? He certainly cares, right? Because look, it's raining, and he's wearing something. So I think he does care. He's wearing a leaf, right?
He took the umbrella too, didn't he?
Yeah. So, and the next question is, does Totoro care about space weather? I want to hear. I want to hear your imagination.
I don't know if there's any evidence.
You don't have any. You don't have any evidence. So someone has different ideas, different opinions.
I reckon he enjoys the Aurora.
He will enjoy the Aurora. Yeah, I guess so too. Yeah. So
Yeah.
Space maybe not because all
he already has. He has the answer already. Maybe. Yeah. He has to care, right? Because the Neko bus is using electricity.
Is it?
So when you have a blackout, it doesn't run.
It's magical.
Well, yeah. So.
I think maybe for one more question. Go ahead.
Right?
Yeah.
Going back to Auroras,
Yes.
the prevalence hypothesis was that it was due to charged particles being caught in the tail of the magnetosphere. And then when
Also.
the tail snaps and
Yes.
recombine,
Yes.
accelerated the particles to the jet. Is that still the prevalence hypothesis, or is there something that has
That's true. You are asking. Yeah, that's extremely professional. That's extremely professional. That's actually the right answer. And so
that's still the prevalent.
yes, yeah.
Which
So,
explains why we see
sorry.
it at night and not during
So, yes. So this video, actually, anyone who had a sharp eyes maybe had a better observation here. And yes, yeah. So now watch out at the end. So they go to the tail. So here we say the tail. This is the tail of magnetic field. So you can see. Pay attention now. So this is how the main energy come in, actually, and then they cause aurora. So yeah, the magnetic field, we call it reconnection. So at the tail, they are all this, and then the solar wind somehow also has some magnetic field. Then they get reconnected, they get closed, and then they get snapped in towards the Earth, and cause the aurora in polar regions.
And in fact, I think one of the ESA missions detected monopoles in space.
Right.
So
right.
before they reconnect.
Yes, yeah. There are quite a few satellites now. Yeah, HIMARS and MMS, and they are all trying to observe directly this process. Yeah.
Okay,
Great.
that's time. So please give another round of applause.
Thank you so much.